Good afternoon, everybody. AI-powered language models like ChatGPT, Grok, and Claude have become incredibly powerful tools. Oh, all right. Revolutionizing everything. Okay. Revolutionizing everything from creative writing to business automation. But beneath the surface, these models face a fundamental challenge. And that challenge is efficiency. And today, I'm going to talk about how we can make AI models faster using state-space models as an alternative to transformers. And we'll talk to a couple things. We'll talk about transformers and why they are computationally expensive, and how state-space models provide an alternative method to process language. And we'll talk about my research on extracting finite state machines to make AI more interpretable and lightweight. And by the end of this talk, I hope to show you why state-space models matter and can be proved to be an alternative. No, there will be a exciting approach to better, more efficient machine learning. So, click. Hold on. All right, cool. So let's take a step back and talk about how we process language. Whether we are speaking, writing, reading, or listening, our brains are constantly shifting between different mental states. And we interpret meaning, we understand language, we try to anticipate what comes next in a sentence based on the context. And this happens quite naturally for us humans, but for AI models, capturing these shifting patterns is quite a challenge. Traditionally, finite state machines have been used to capture structure and structured language patterns. And what a finite state machine is, awesome. So what a finite state machine is, it's a system that contains a, oh, wow, back, okay. What a finite state machine is a system that contains a fixed number of states with rules that determine how we move between these states based on input. And an example of a finite state machine is a subway turnstile. So subway turnstile has two states, locked and unlocked. You insert a coin into the turnstile, it unlocks, and you push the bar on the turnstile, it locks again. So we can think of language in the same way. Certain words or phrases change our state of our understanding as we process them. But human language is far more complex, far more flexible, and far more context-dependent than a turnstile. So there's a million-dollar question. And a million-dollar question is, how do we build models to capture this deep richness in human language while keeping things structured? So let me tell you about how things are being taken care of right now. So most AI language models today are built using a neural network architecture called the transformer. And transformers are incredibly powerful because they use an attention mechanism to compare every word in the input text to every other word. And that gives us deep contextual understanding, but it comes at a cost. For one thing, transformers don't have an explicit state representation, and what I mean by that is they do have internal states, but those states aren't represented as discrete transitions in the same way that an FSM does it. When they process text, they process all the text in parallel, which isn't the same way that, so it doesn't track structured state transitions the same way that an FSM will do it. And also, when they process text, they constantly recalculate the relationships between each word in an input sequence, which makes things not only very complicated to interpret, but also computationally expensive, computationally inefficient. So let me talk about state-space models. Wait, let me take a step back. I just forgot one more thing. So one more thing I want to mention about this. So if we were to try to extract an FSM from a transformer, we'll have a very difficult time with it because it stores its information in a way that actually lines up the way FSM stores information. Its information is, its knowledge in the transformer is distributed across different layers of the neural network. So let me talk about state-space models. So state-space models isn't something that's new. It's been used for decades in fields like engineering, finance, and economics to describe how systems evolve over time. And at the core, a finite state machine uses a series of equations to track the dynamics of a system and try and predict how new inputs in a system will react, what outputs it'll produce in response to inputs. So in recent years, state space models have been embedded within deep neural networks to create new type of AI models that work differently from transformers. And one of those models happens to be one that was developed in 2023 called Mamba. Mamba provides three key properties that make it give it an advantage over transformers. And the first property is, recurrent inferencing. Okay, there was supposed to be a little animation there, but it's fine. Okay, so recurrent inferencing. So that means, what I mean by that is Mamba processes input. So unlike transformers, where it basically takes all the input tokens and processes them all at the same time, Mamba processes its inputs one step at a time. And it's really similar to how we as humans read by absorbing words sequentially. So this allows Mamba to basically update its state as new information comes in. This makes it much more faster than transformers. So the second property has to do with how it actually processes memory. So unlike transformers, which basically stores all its input sequences and basically attends to each word individually, Mamba actually compresses its entire history into a structured state matrix. And this is basically like how it's like, another way to think about it is how we take notes while we're reading a book, where we capture the most important things in a text without recording everything down. And that allows Mamba to capture a global state, a global context of its entire history without consuming excessive memory. And the third property is selective retention of data. So one of the challenges with traditional state space models is that they treat every piece of input equally. And this is actually how human reasoning works. So in language modeling tasks, certain words or phrases matter more important than others. So for example, if someone were to ask you what is the capital of France, the word France actually is more important than the word the or of. So to fix this, Mamba actually selectively picks which parts of it it remembers. So why it does that is that it filters out some of the less important details over time, as it processes the input while boosting its memory of other information. And this gives it the capability of context. It gives it the ability to actually be context processing. So it allows it to do things like select pieces of information from a text, or even learn from a few examples, similar to the way a transformer works. So let's take a look at how Mamba compares to transformers in terms of speed and accuracy. So I performed a series of benchmarks of Mamba and other transformers of similar sizes and complexity. I ran it against several benchmarks that measure common sense reasoning, inference, and text comprehension capabilities. And I found that Mamba performs just as well or better than transformers on these tasks. And that's primarily due to its structured state representation, which not only helps reduce overfitting, but also allows it to represent certain patterns in the data long-range dependencies in the input more precisely and compactly than the attention mechanism in transformers. So I also ran several speed tests on the same models, and I found that while transformers how I want to say it, while transformers scale quadratically, exponentially as the input lengths grow, Mamba speed actually scales linearly. And this has a number of practical benefits. One of them is the ability to, for companies that are trying to scale, deploy AI models at scale, this speed efficiency allows them to save a lot on cloud or hardware costs. The other benefit would be enabling companies to deploy their AI models on lower commodity hardware, unlike transformers that typically requires more higher-end GPUs to run. And then the third benefit is for tasks that require processing long documents or analyzing large amounts of data, you can actually do this more efficiently without having to worry about excessive memory consumption or high latency. So why am I talking about this? What's the point in all this? So since Mamba can efficiently process information in a structured way, and it has and while keeping a compressed, a structured state representation, this makes it a really good candidate for finite state machine abstraction. So my ongoing research at Kwaai is to develop methods to extract finite state machines from Mamba to approximate its performance on certain modeling tasks. And this gives us a couple of things. So my goals are to acquire 3 things. So my first goal is to develop some tools that allow us to actually get some sort of more interpretability into how Mamba and other language models similar to it work. Because right now the state of AI is like we have a big black box. We have no idea how it works, how anything works. So this will, by having a finite state machine, we'll be able to actually study the insides of these language models and see how they work. And the other benefit is when we can, it gives us a layer of verifiability. So we can actually see if a language model, Mamba, is actually working the way we want it to. And this would be really important in applications safety critical applications where like healthcare or any high stakes environment where making it like verifiability is really important. We don't want things to blow up in our face or people to die by using these AI models. And then the third thing is efficiency. So if we can get a model that closely approximates Mamba's behavior, we can actually replace it. We actually replace Mamba and in those applications where we can get even more efficiency out of it. So to take things off, we talked about transformers and why, despite being very powerful, they're computationally inefficient. We talked about state space models and Mamba and how they provide a more alternative way to process information while keeping things very efficient. We talked about some benchmarks, some experimental results that showed that Mamba is faster than transformers in certain tasks. And we talked a little bit about my research on extracting finite state machines to understand how to improve these models further. So Mamba is an exciting, to me, represents a really exciting path towards making AI more scalable and efficient, and an exciting way to make AI that is faster and accessible to not just big tech, but everyone as well. And if you'd like to contact me or get involved in the research, feel free to grab my information, and we'll see what we can do. You can all help with the research, so any help you can provide would be great. And I'm also available later during the networking reception later this evening if you want to talk there. Thank you.
That was fantastic. Thank you so much, Daryle.